And ladies and gentlemen, welcome once again to the Simpkins Physics Corner. Today is all about the force, or I should say force, but let's get into it. All right, what is a force? A force is a push or a pull. It's measured in newtons. If you didn't know, that's that guy right there, Isaac Newton. And it's a vector, so that means it has both magnitude and direction. Oh yeah, it's true, it's true. And there's four main types of forces that I want you to know about at the end of this lesson. So for this year, it's week 19, async 2 representing forces. Check your notes and follow along. You'll probably have to hit pause several times along this video. That's okay. Don't forget, you can change the settings to speed me up. Who can do that? Or slow me down if you need to as we go through our notes. At the end of this, you should have the 2 pages of notes for how to define the forces, draw the forces, and how to draw free body diagrams. So let's get into it. Free body diagrams. Ooh, my favorite. What are they? Well, they are diagrams that let us represent the forces acting. So let's start with normal force. Again, if at any time you need to pause this video, feel free to do so. But a normal force is a pressing force towards the object it's supporting. So right now I'm sitting on a chair. That chair is pushing up on my butt. The chair is exerting a normal force on my butt because it's a pressing force over a surface area that is pressing towards me, the object. That's a normal force. If you stand on the floor exerts a normal force up on you. If a box is sitting on the floor is exerting a normal force on that box. And the thing we need to know about this is that it's always perpendicular to the surface. All right, so if you're on the floor, then the normal force is straight up in that direction. But if you're on a ramp or on like a sloping hill or something, you notice this normal force is now pointed up and to the side a little bit. That's perpendicular to the surface. So it's always drawn perpendicular to the surface and away from that surface. That's how we draw normal forces. So a book sitting on a table or a kid going down the slide could be represented by these blocks, these free body diagrams with the forces indicated, the normal force as we see those two right there. So that's normal force. Again, if you need to pause at any time to keep up with the notes, feel free to do so. Gravitational force, all right? It's an attractive force between any two objects with mass. So far, we've just talked about gravity as being straight down, and that's because in our reference frame here on Earth or in the physics lab or whatever it is, now, of course, we know there's more details to it than that. Like if I wanted to draw the Earth and draw a U, okay? What's really going on here is that your mass and the mass of the Earth cause an attraction. We don't know really why, but they do. And that's the force of gravity. And so if you're going to draw the force of gravity or represent it on a free body diagram, you always draw it straight down from the center. That's because the force of gravity acts on objects' centers of mass. And this is where you see the first distinction. Consider and watch and look at these two pictures right here. Where's my thumb? There's my thumb. Those two pictures right there. My thumb got eaten for a second. The force of gravity is straight down. In the previous slide, the normal force is perpendicular to the surface. So people confuse this right away. Notice the normal force is perpendicular. It's perpendicular. Over here, gravity doesn't care what surface you're on. It's always pulling you straight down, at least on a reference frame of Earth. And so we always draw the line straight down from the center of the object. So an example, here's your box sitting on a table again. Here's a box sliding down a ramp. Force of gravity would be indicated straight down in both cases. How about tension force? All right, you got to pay attention. Yeah. So the tension force is a stretching, like if you have a string, a rope, you can have a spring. Let's say you're pulling something along. Maybe you went sledding recently, you pulled your sled along. That's the tension force. And it would be drawn like this with a little FT there. So it's always away from the body. And when we say the body, we mean the object that's exerting, that force is being exerted on. And it's always drawn from the edge, kind of like that. So if you're pulling a box with a rope, it might look like that. If you're having a tug of war, maybe this is the flag or the rope in the middle, then you have tension pulling one on either side. And so that's how the force of tension would be drawn. Again, if you need to pause at any time, do so, catch up with those notes. How about friction? All right, friction is anytime you have rubbing between two surfaces. We'll talk about static and kinetic friction later this year. But friction, what we can say is that it's a force that always, and I've been very careful about this definition, opposes motion. Friction opposes motion, okay? And in the case of a box going across the floor, let's say I was pulling something across the floor. Which way am I moving? That way. Which way is friction? Opposing the motion. Now, here's the equation for it. We'll see that on the equation sheet, and we'll work with that as this unit unpacks a little bit. But let's look at friction opposing motion in another way. What if I put something on a ramp, and it just sits there? Well, if it's sitting there, we know it wants to slide down, right? But it's prevented from doing so because of the force of, you guessed it, friction. Okay? And so here you're at rest, but we know the direction of friction because it's opposing the motion that wants to happen or would happen if we didn't have enough friction. So friction opposes motion in the sense that when you're moving, it's acting in the opposite direction. or if you're not moving, it's the thing that's keeping you from moving. All right, so that's how we define friction. Now, at the bottom of your notes, you'll see applied force. So I guess I should just add that in here real quick. All right, but applied force is basically if you're doing a physics problem and you're not sure what to call it, you call it applied force. So if it says a person pulls a box with a force of 30 newtons, okay, you could just call that applied force. All right, so that's just like the catch-all. So on your notes as you're looking at them, if you see the word applied for applied force, we would draw like FA, and that's just if you have something, a push or a pull that you're not really sure what kind of force it is, you can call it FA, you can call it the applied force. Now, as you flip to the next page of your notes, you're going to see the free body diagram worksheet. And here is where I want you to practice identifying the kinds of forces that we just defined. And can you draw them on a free body diagram? So I'll get you started with a few examples. All right, object lies motionless. Now, we're going to assume, unless they tell us we're in outer space, that we're not in outer space, which means there's always force of gravity. So if you're starting an FBD, a free body diagram, it's just a picture that shows you what forces are going on. You can always draw the FG. It's always the easiest one to do first. So hold on, let me come back here real quick. All right, so we got FG like this. FG goes down. And of course, there'd be a normal force from the floor pushing up on you. So this stuff is pretty straightforward, pretty easy. Now, we talked about Newton's first law, inertia, and it says that objects that are moving stay moving and objects that are at rest stay at rest. It means you need an unbalanced force to change something's state of motion. And this has a big implication. This means that constant speed tells us something really important. It tells us that there's either no forces acting in a particular direction or that the forces acting in that particular direction are balanced or equal out. And we'll unpack this as we go through our lessons later this week. All right? But at a constant speed, what that means is there are no forces to the left or to the right because it's moving at a constant speed. It will just keep moving unless acted on by an outside force. So it's important to, whenever you see the word constant speed, that should trigger you there. Forces are balanced. Something is important that's going on there with constant speed. This one's looking the same, though, because look, the forces are actually exactly the same as the first diagram over here. There's only the force of gravity down, the normal force straight up or perpendicular. Now, when you slide down a ramp, remember, the normal force is going to be perpendicular to the ramp. So notice that it's not straight up. It's kind of tilted. It's tilted such that it's perpendicular with the ramp, but the force of gravity is still going to be acting straight down. So you notice they're not quite in the same direction. It's going to be important later as we get into more of the details. Here we got a rope, so that's a FT, and down here is a FG. All right, so another little example. And so I want you guys to try out the rest of these, and I'm going to pause the video here, and then you can unpause after you give them a shot. Check your answers, see how you're doing with this force thing. 3, 2, 1. Here is a little answer key for you guys to check your work. So by the next time I see you, or if this happens after the lesson, just make sure this all goes into your packet, stash it there. Because I'm going to be asking you to submit a free body diagram here this week. So make sure you know how to draw normal force, tension force, gravitational force, and frictional force. Call those the big 4 forces. And until next time, this is Mr. Simpkins in the Simpkins Physics Corner.